Today we will discuss about the statistical thermodynamic treatment of transition state theory. Okay, in the previous class we discussed about what is activated complex and what is transition state. Okay, and how this activated complex is very different from an intermediate, and also we stated and discussed what are the different postulates or assumption of transition state theory. Today we will discuss about the mathematical formulation of transition state theory. Okay, as I told you in the previous video, there are two ways of formulation of transition state theory. One is the statistical thermodynamic treatment, where the rate constant of a reaction is expressed in terms of the partition function. Okay, you all know that the partition function forms a very important quantity in statistical thermodynamics. Okay, so other treatment of transition state theory is by using uh, the various thermodynamic quantities such as entropy, enthalpy, free energy, which is called as classical thermodynamic treatment of transition state theory. Okay, I advise you to again to go through the previous two videos about the transition state and activated complex, and the video where I discussed the postulate of transition state theory. Okay, so today we will discuss about the statistical thermodynamic treatment, and end of the video I'll just give a brief introduction to the thermodynamic treatment or classical thermodynamic treatment, which would be part of my discussion for the next video. Okay, so let us consider a bimolecular reaction. Okay, let us consider a bimolecular reaction A plus B giving products. Okay, A plus B giving products. Now, according to transition state theory, how can we write this reaction? Okay, according to transition state theory, any reactant molecule before forming product, it has to pass through a state called transition state, where a complex called activated complex is formed. Okay, so according to transition state theory, these reactants has has to form initially an activated complex represented by the symbol X double dagger. Okay, and this activated complex passes on to form the final product. Okay, according to one of the assumption of transition state theory. Okay, that is why I told you please go through the assumptions or postulates again before this video. Okay, so according to transition state theory, though there is no equilibrium between the reactants and the activated complex, but for the sake of calculation of the concentration of the activated complex, we are assuming that there is some sort of equilibrium between the activated complex and the reactant. So this is a type of pseudo equilibrium which in reality does not exist. Okay, so let us assign K dagger as the equilibrium constant for this process, which is called as activation. Okay, so this process is called as activation because it involves the formation of the activated complex. And let us assign the rate constant for the overall reaction. The rate constant is K. Okay, so this equilibrium, remember, this is only used for the purpose of calculation of the concentration of the activated complex. Why the concentration of activated complex is very important here? Again, if you go back to the postulates of transition state theory which we learned in the last class, according to one of the postulates, the rate of a reaction according to transition state theory is directly proportional to the concentration of the activated complex, and the concentration of the activated complex according to this theory is obtained or estimated by using the equilibrium theory. Okay, that is why I have shown this symbol equilibrium, which in reality does not exist. So it can be shown that for such a reaction, according to transition state theory, the rate constant, for the above reaction is given by K, rate constant K is equal to K into D, that is Boltzmann constant, into temperature divided by H, the Planck's constant, into Q dagger, okay, divided by QA into QB into e to the power minus delta E divided by RT, okay, which can also be written as KB into T divided by H into K dagger, okay. So this is the expression for the rate constant of a biomolecular reaction according to transition state theory. Here the symbol Q represents what is known as partition function. Okay, what is partition function? It is the number of states, okay, that a system provides at a particular temperature and at a particular volume. So the number of states, accessible state at a particular temperature and volume for a system. So QA and QB are the partition function for the reactants A and B, and the Q dagger here is the partition function of the activated complex. Okay, we will discuss about this partition function, especially this partition function, in detail when I go through the derivation. Okay, and delta E is nothing but the change in the ground state energy or the zero point energy when the reactants is converted to the activated complex, which is almost equivalent, okay, to activation energy of the reaction. So this is the expression for the rate constant according to transition state theory. So let us now derive the expression which I have mentioned here. Okay, so, according to transition state theory, any reaction has to pass through this simple mechanism that I have given here. The reactants, before forming a product, has to form an activated complex. Though there is no equilibrium between the reactant and the activated complex, however, in order to calculate the concentration of the activated complex, we are assuming that there is an equilibrium between the reactant and the activated complex, and the equilibrium constant, okay, not for the entire reaction. This is the equilibrium constant only for the activation process, K dagger, according to the definition. Okay, how do you define equilibrium constant? It is the concentration of the activated complex divided by concentration of the reactants. Okay, concentration of the reactants. Please do remember that this expression for equilibrium constant is applicable only for reaction taking place in gas phase or for dilute solutions. Okay, for concentrated solution, then we cannot use concentration, we have to use activities. Okay, however, for dilute solution we can use the concentration, okay, as the correct way of representing these reactants and uh, activated complex. For gas phase, what we have to do is concentration has to be replaced by partial pressure. So this reaction that we are developing now is applicable for gaseous reaction and for dilute solutions. Okay, so this is the expression for equilibrium constant. But we have studied, okay, in our earlier semester, okay, in statistical thermodynamics, how to express the equilibrium constant in terms of partition function. You please remember all the thermodynamic quantities such as enthalpy, entropy, free energy, and even equilibrium constant can be expressed in terms of the partition function. So that gives a relation between classical thermodynamic quantity and statistical thermodynamic quantity. Okay, we will not derive this equation again. We have derived it in our previous semester, so we will directly use that expression. Okay, so the equilibrium constant can be expressed the equilibrium constant can be expressed in terms of the partition function. Okay, it can be expressed in terms of partition function. How? The equilibrium constant, which is nothing but, according to equation 1, is concentration of the activated complex divided by the products of the concentration of the reactants, is given by Q dagger or double dagger. Okay, see here. Here the symbol is not written as a subscript, it is written above as a superscript. Okay, in the previous expression, okay, that I had written for the expression for rate constant k, the symbol for partition function of activated complex was written like this. So there are different notations I am using which carry different meaning. So what is this q dagger and what is this q dagger, what do they really mean, I will explain. Okay, so it is q dagger, which is the partition function, the overall partition function of the activated complex, divided by the partition function of reactant A into partition function of reactant B into e to the power minus delta E divided by RT into e to the power minus delta E divided by RT. Let us take it as equation number 2. So where did we get this equation from? This equation we got from statistical thermodynamic treatment, okay, where the equilibrium constant is given by this expression. Now let us go back to one of the important assumption of transition state theory. Okay, I already told you. Let me draw the potential energy diagram for a reaction. Okay, so this is potential energy, this is the reaction coordinate. Okay, let me draw a typical potential energy diagram where a reactant R is converted to product P, and this reactant passes through a state called as transition state where this activated complex is formed. Okay, say for example this activated complex is having the structure something like this. Okay, and the example I'm giving here is no way concerned to this particular reaction. I'm giving some general example. Okay, so the structure of activated complex is something like this: A, B, C, D, E. Okay, some complicated structure where there are four bonds. Okay, four atoms connected to the central atom A. So here this bond between and A is a new bond that is being formed during the reaction, and this bond AB, which is an old bond between the reactant, is partially broken. Okay, so when the reactant is converted to P, product P, so this bond is progressively broken and formed, and this bond is progressively broken. Now for such molecule, which is of course non-linear here, there are 5 atoms. So it means there are 3 into n, that is 3 into 5 minus 1, uh, which is 14, or if it is 3n minus 2 formula, 3 into 5 minus 2 is equal to 13. So there will be either 14 or 13 degrees of freedom, vibrational degrees of freedom, depending on whether the molecule is linear or non-linear. Okay, uh, I think I made a mistake. Okay, I made a mistake here. It is 3 into n minus 5 or 3 into n minus 6. Okay, so it will be 15 minus 5, 10, or 15 minus 6, 9 vibrational degrees of freedom, depending on whether the molecule is linear or non-linear. Okay, so though there are 10 or 9 different vibrational degrees of freedom, only one particular vibrational degree of freedom is determinantal, okay, or it is very significant here for the formation of the product. And which particular vibrational degree of freedom? It is that vibrational degree of freedom corresponding to this bond which is progressively being broken. So the vibration of the bond AB, okay, is very important. So out of 10 or 9 vibrational degree of freedom, this vibrational degree of freedom is very important. And according to one of the postulate of transition state theory, this is a very loose vibration with no restoring force. What does that mean? I will not explain it again here. Please go through the previous video that I have discussed. So this particular vibration is a very loose vibration with no restoring force, and uh, the speed with which the activated complex will be converted to product will depend on the frequency of that particular vibration, and also it depends on the degree of freedom related to that particular uh, vibration. Now according to one of the postulate of transition state theory, it is possible to separate the degrees of freedom corresponding to this particular vibration from the total degree of freedom, total vibrational degree of freedom. This is one of the assumption of transition state theory. I repeat, according to transition state theory, it is possible to separate that one particular vibrational degree of freedom, okay, corresponding to this loose vibration in the activated complex from the overall vibrational degree of freedom. How that can be done? That can be done by using the principles of partition function. Okay, we in the previous semester, when we studied about partition function and its characteristics, we have observed that for a given system, the overall partition function is always the product of individual partition function. So the partition functions are always multiplied. So here also we are assuming that, okay, the overall partition function corresponding to the vibrational degrees of freedom especially, okay, or overall ಎಲ್ಲಾನು ತಗೊಂಡ್ರು ಕೂಡ overall vibrational overall partition function corresponding to all degrees of freedom can be written as product of two partition functions. One, the partition function corresponding to loose vibration. Second, the partition function corresponding to all uh, degrees of freedom except corresponding to the loose vibration. Okay, so according to transition state theory, or one of the postulates, it is possible to separate that one particular degree of freedom corresponding to the loose vibration with no restoring force. Okay, it is possible to separate that one particular degree of freedom corresponding to loose vibration from the other degrees of freedom in the activated complex. And where is this activated complex formed? This activated complex is formed at the peak of the energy potential energy diagram, which is called as a call. Okay, so how do you write this mathematically? Mathematically we will write that is Q dagger. Okay, now you should understand what is Q dagger. It is the overall partition function is equal to Q, okay, Q dagger, which is the overall partition function except the partition function of this loose vibration, okay, into kb into t divided by h into new dagger. What is this kb into t by h into new dagger? This kb into t divided by h into new dagger is the total partition function corresponding to this loose vibration. Okay, so we have here eliminated the derivation of this term. Okay, it is possible by using statistical thermodynamics to derive this expression, which we will eliminate here, and we'll keep the things very simple. So the total partition function of the activated complex is the product of the partition function, the total partition function, okay, which does not involve the partition function for the loose vibration. Okay, so into this partition function corresponding to loose vibration, which is given by kb into t divided by h into new dagger, and here new dagger is the frequency of this particular vibration, which is called as loose vibration with no restoring force. I repeat, the total partition function of the activated complex is equal to the partition function not including the loose vibration into the partition function corresponding to the loose vibration, which is given by this expression, and nu dagger is the frequency of this particular loose vibration. Okay, so equation 2 here, this q dagger can be written or replaced by equation 3. So let us rewrite equation 2. Therefore equation 2 can be written as concentration of X dagger divided by concentration of A into concentration of B is equal to Q dagger, okay, into Kb into T divided by Kb into T into Q dagger divided by Qa into Qb into H nu into e to the power minus delta E divided by RT. Okay, so here the total partition function is written as the product of the two partition functions according to the postulates of transition state theory. Okay, so let us rearrange equation number 4. Okay, let us rearrange equation 4 in such a way that only concentration of X dagger and this frequency, okay, this is new dagger, okay, this new dagger is on one side of the equation, that is LHS. So we'll take this new dagger to LHS. So new dagger into concentration of X dagger is equal to Kb into T divided by H, okay, into Q dagger divided by Qa into Qb into concentration of A into concentration of B into e power minus delta E divided by R into T. Okay, so this is the expression that we obtained after rearranging equation 4. Okay, let us make some simple argument here. Okay, if you look at the LHS of this equation, you have two terms in the LHS. One is the concentration of the activated complex, the other expression is the frequency of that particular vibration, which is nothing but the loose vibration. And I already told you, okay, it is the frequency of the loose vibration which corresponds to zero restoring force that is very important or detrimental for the formation of the product. It is the frequency of this particular vibration uh, which is important for the formation of the product. So the LHS of the reaction can be argued as nothing but the rate of the reaction. Okay, ನಾನು already ಹೇಳಿದ್ದೇನೆ, rate of the reaction according to transition state theory is directly proportional to concentration of the activated complex. So here you have concentration of the activated complex, okay, which is directly proportional to rate, and also you have the frequency corresponding to loose vibration, which is also a factor that decides the rate of the reaction. So this product, okay, both the factors are directly proportional to the rate. So we are arguing that the LHS of this equation is nothing but the rate of the reaction. So the LHS of equation 5 is nothing but the rate of the reaction. Therefore, rate of this reaction is Kb into T divided by H into Q dagger divided by Qa into Qb into concentration of A into concentration of B into e to the power minus delta E divided by RT. Okay, so this is the expression for the rate of the bimolecular reaction A plus B giving product as predicted by transition state theory. Remember, we are interested in obtaining an expression for rate constant, okay, that I had written earlier. So let us write an expression for rate constant. We know that, okay, for a reaction A plus B giving product, so this was the original bimolecular reaction A plus B giving product. For such reaction, if K is the rate constant, then the rate of the reaction generally is written as rate constant into concentration of A into concentration of B. This is the general way of writing rate of a reaction. Okay, according to law of mass action, rate of a reaction is rate constant into concentration of reactants. So equation 6 is also an expression for rate of the same reaction according to transition state theory. So comparing equation 6 and 7, it is possible to obtain an expression for rate constant. If you carefully look at the RHS of the equation, in the RHS, here you have concentration A into B, here also you have concentration A into B. So all the terms in the RHS except this A into B is nothing but rate constant. So equation 6 ಮತ್ತು equation 7 compare ಮಾಡಿದರೆ, especially RHS ಅನ್ನು compare ಮಾಡಿದರೆ, it is possible to obtain an expression for rate constant. Okay, so comparing the RHS right hand sides of equation 6 and 7, one obtains an expression for K, that is K is equal to Kb into T divided by H into Q dagger divided by Qa into Qb into e to the power minus delta E divided by R into T. Okay, so this is the expression that I had written earlier. It is the expression for the rate constant of a bimolecular reaction A plus B giving product, which is Kb into T by H, where Kb is the Boltzmann constant, T is the temperature, H is the Planck's constant, into Q dagger. Okay, please understand the significance of this Q dagger. Q dagger is not the total partition function of the activated complex, it is the partition function of the activated complex obtained after excluding the partition function of the loose vibration. Okay, so this is the total partition function, but we are excluding the partition function related to loose vibration, divided by partition function of A into partition function of B into e power minus delta E by RT, where delta E is the change in the 0-point energy of the reactants and the activated complex, which is roughly the activation energy of the reaction. So this is the expression for the rate constant of the reaction. Now if I consider this term, okay, so I will rewrite equation number 1, equilibrium constant is equal to concentration of X dagger divided by concentration of A into concentration of B. This is equation number 1. And according to equation number 2, we learned how to express the equilibrium constant in terms of partition function. So this is Q dagger divided by Qa into Qb into e power minus delta E by RT. Okay, so this is equation 2. So this is equation 1 or 2 is the expression for equilibrium constant. So you can note down there is a difference in the symbol. This is the total partition function, this is the total partition function excluding the partition function of loose vibration. But if I leave this, rest of the terms in this expression is same. Okay, other than this Q dagger, the rest of the expression is almost same. So what do we do here is we approximately, okay, assume that this term here, okay, is roughly equal to the equilibrium constant. Okay, strictly speaking, this is not equal to equilibrium constant because equilibrium constant involves the total partition function, whereas here in this term this is not the total partition function of the activated complex, but still as a rough approximate or a rough estimate we assume that this is roughly equal to the equilibrium constant according to equation 2. So this equation 8 can be roughly rewritten as okay, K, the rate constant of the reaction, therefore K is equal to Kb into T divided by H into K dagger. Okay, so this is a well-known equation in transition state theory, which gives the relation between K, the rate constant of the reaction, and K dagger, the equilibrium constant for the formation of activated complex. Okay, so this is a rough approximation or estimate. So rate constant of the reaction is equal to Kb into T by H into equilibrium constant for the activation process. Okay, and as I already told you, this equation is applicable for gaseous reaction and for reactions with very low concentrations, that is reactions carried out in very low concentration, that is dilute solutions. Okay, so this is about the statistical thermodynamic treatment of transition state theory. But the problem with this treatment is, here the rate constant is expressed in terms of partition function of the species involved, that is partition function of the reactants and partition function of the activated complex. Evaluation of partition function is very simple if the reaction is taking place in gas phase. So if the reaction is taking place in gas phase, calculating the partition function is very simple. But if the reaction is carried out in solutions, which is the most general phenomenon, okay, most of the chemical reactions are carried out in solutions. So for reactions carried out in solution, evaluation of partition function is very difficult, and we know that for solutions it is rather the chemical thermodynamic quantities, classical thermodynamic quantities such as enthalpy, entropy, internal energy, free energy are the ones that can be easily evaluated. So for solutions or reactions in solution, it is always better to express the rate constant in terms of classical thermodynamic quantities such as free energy, enthalpy, entropy, rather than partition function. So that is the necessity for one more treatment of transition state theory, that is in terms of classical thermodynamic treatment. Okay, so what is this classical thermodynamic treatment? I will give a rough introduction to this classical thermodynamic treatment. However, in detail we will discuss it in the next class. Okay, so this classical thermodynamic treatment originates from the statistical thermodynamic treatment. Okay, again we are not uh, the approach that we use for classical thermodynamic treatment is not from basic level. Again, already we have the statistical thermodynamic treatment, so we are just, okay, continuing the statistical thermodynamic treatment, where in we somehow, okay, in the statistical thermodynamic treatment we are trying to insert this classical thermodynamic treatment. How, that I will explain briefly. Okay, according to transition state theory, the rate constant of a reaction K is given by Kb into T divided by H into equilibrium constant. So this is according to transition state theory. Okay, now to this equation, how it is possible to introduce any thermodynamic factor or thermodynamic variable. You have different thermodynamic variables such as free energy, enthalpy, entropy, internal energy. So is it possible to introduce any one of the thermodynamic function into this equation? The answer is yes, because here we have equilibrium constant, and this equilibrium constant is directly related to one of the chemical thermodynamic parameter, that is free energy. Okay, we know according to want of isotherm, delta G naught, okay, the change in the standard free energy of the reaction is equal to minus RT into ln K, okay, where K is the equilibrium constant for the of the reaction, which can be rearranged and written. Therefore, K is equal to e to the power minus delta G naught divided by R into T. This is the relation between the equilibrium constant and the change in the standard free energy of the reaction. So, how can you write therefore K dagger? K dagger is not the equilibrium constant for the entire reaction, it is the equilibrium constant for the formation of activated complex. What does it mean? I will rewrite this reaction. Okay, any reaction according to transition state theory, okay, the reactants has to first form activated complex and then it forms product. Okay, so it is assumed, okay, that there is an equilibrium only for the sake of calculation of concentration of activated complex. So there is an equilibrium between reactants and activated complex, and K dagger is the equilibrium constant for the formation of the activated complex. So this K dagger is not the equilibrium constant for the entire reaction, it is equilibrium constant for this particular process. So K dagger can be written as e to the power minus delta dagger of G naught divided by R into T. What is this symbol? Delta G dagger is nothing but the change in the standard free energy. It is the change in the standard free energy when the reactant is converted to the activated complex. So change in the standard free energy for the activation process, which is nothing but called as free energy of activation. Okay, so this delta G naught is not the change in the standard free energy of the entire reaction, it is only the change in standard free energy for the activation process. Okay, so it is called as change in the standard free energy for the activation process, or simply it is called as free energy of activation. Okay, so if I take this equation as equation number 2 and substitute in equation number 1, okay, then the rate constant K is equal to Kv into T divided by H into e to the power minus delta dagger G naught divided by R into T. Okay, so we have paved a path, okay, where we have introduced a thermodynamic quantity into the rate constant. Okay, and now this expression can be written in different forms where we can introduce several other thermodynamic quantities such as enthalpy, entropy and internal energy. So this original equation obtained from transition state theory is now written in terms of thermodynamic factors. Now in the next class we will continue this discussion and try to obtain an expression for rate constant in terms of various thermodynamic quantities, and we will also try to understand the procedure for evaluation of all these thermodynamic quantities. Okay, how to calculate the enthalpy of activation, entropy of activation, and free energy of activation, okay, and energy of activation by using this classical thermodynamic treatment.